So let's look at some examples of multiplying and dividing radicals. So to begin with, if we multiply the square root of 2 times the square root of 7x, we are allowed to multiply the items underneath the radical. If one was a square root and one was a cube root, we could not do that. But since the index are the same on each of these, we simply multiply what's alike or multiply what's under the radicals, and we can simplify that. That's true whether it's a square root or if we have a cube root of 3x times a cube root of 6xy. Since they're both cube roots, then we can multiply what's underneath. 3x times 6xy. So 3 times 6 is 18. X times x is x squared. And we also have a y. Now, in the first case, 14 is not a perfect square. In the second case, 18 is not a perfect cube. And neither of those can be simplified any farther. And that is a good use for multiplying square roots. But this rule of where we can write different radicals as a single radical, often we use it to break apart radicals. For example, if we have the square root of 18, 18 is not a perfect square, but it does contain a factor that's a perfect square. 18 is 9 times 2, and 9 is a perfect square. So we could rewrite this as the square root of 9 times the square root of 2. Well, the square root of 9 is 3, so we simplify it. 2 is not a perfect square, so we leave it as it is. So this is an important use of this property. Lets us simplify radicals as we have larger values. Now remember, anytime we have something squared under a radical, that could also be considered x times x. So if we're taking a square root and we have the same factor twice under the radical, the square root and the square undo each other. So we have that factor twice, it's squared, those undo each other, so we get that factor out one time. If we have square root of k squared, the square root and the square cancel. So if we had something written like this, we have that same factor twice. We could write it as k squared, but if that factor occurs twice, then we pull that out from underneath the radical. Now, why do I say that? As we get into larger numbers, it's not always obvious what the greatest factor is that's a perfect square, and especially with variables. So with 24, let's factor it into its prime factorization. 2 times 12. 12 is 2 times 6. 6 is 2 times 3. So underneath the radical, we have 1, 2, 3 2's, and a 3. X cubed, we could write as x times x times x. So as on the previous slide, we demonstrated, anytime we have the same factor twice underneath a square root, we bring that factor out. So we have a pair of 2. We have a pair of x's, so we bring out an x. And everything that's not in a pair stays underneath. That 2 is not in a pair, that 3 is not in a pair, so we're left with a 6 underneath. And this x here is not in a pair, so it stays underneath. So we're left with 2x square roots of 6x. So if you're still at, why did we pull a 2 out here, or why don't we just write 1, 2 out front? We have 2 2's radical, So the square root and the square cancel, leaving us 1, 2. We have an x times an x, so an x squared under the square root. So the square root and the square cancel, so we're able to get an x out. So we have a pair of x's, one comes out. We can do the same thing with a cube. Let's do that same problem, but let's do a cube root. So we factored this in the previous step. 2 times 2 times 2 times 3, x times x times x. So if we have 3 2's, we can bring a 2 out. We only have 1 3, so the 3 stays underneath. We have a group of x's, so we can bring an x out. So 2x times the cube root of 3. Again, 2 underneath the cube root. The 2 outside. X times x times x is x cubed. That's under a cube root. So those cancel, hence we get an x outside. But if it's not in a group, it stays underneath. So let's do one that's got maybe some larger numbers. Let's try 720 x to the 5th, y to the 12th. So 720, that's really big. So let's factor it. If you recognize a factor of 720 that's a perfect cube, you can rewrite 720 as a perfect cube times something else, or we can just completely factor it. 2 goes into 720 360 times. 2 goes into that 180 times. That's 2 times 90. That's 2 times 45. 3 goes into 45 15 times. 3 goes into 15 5 times. So underneath the cube root, we have 2 times 2 times 2 times 2 times 3 times 3 times 5. And then we have x to the 5th, y to the 12th. So if we look at our coefficients, we're taking so we need our comes out. Need the same factor 3 times. So we have 3 2's. So we can get a 2 out. Now this 2 is not in a group, so it stays under. And notice we don't have enough 3's. We only have 2 of those, so those stay under. And we only have 1 5, so that stays under. So as far as our coefficients, we brought a 2 out, and then we're left with, let's see, 2 times 5 is 10, 3 times 3 is 9, 9 times 10 is 90. And then for our x's, well, we have 1, 2, 3, 4, 5 x's, so that's one group of 3, so we bring an x out, but those x's are not in a group, so we put the leftovers underneath. Now, do we really have to write 12 of those? Do we have to write y times y times y times y times y times y times y until we have 12? Well, we could, but let's see if we can think of a simpler way. We're wanting to find out how many groups of 3 can we make if we have 12. Another way of saying that is how many times will 3 go into 12? Well, if I've got 12 cookies and I'm putting them into groups of 3, 12 divided by 3 makes 4 groups. And I don't have any left that are not in a group. So if I have 12 cookies, I have 4 different groups of 3's, and every cookie goes into one of those groups. So the top number tells us how many groups we had, So we get a y for each of those four groups, so y to the fourth. And then we don't have any y's left underneath, so we're not going to put any there. So that would be our final answer. So let's do another one of these. Let's take the fifth root of x to the 11th, y to the 16th. So if we're taking a fifth root, we need something to the fifth power underneath before it will come out. So if we have 11 x's and we want to know how many groups of 5 can we make, we do 11 divided by 5. 11 divided by 5 is 2, or 5 goes into 11 two times. 2 times 5 is 10. So there's 1 left over. So there are 2 groups of x's. Front. And then there was 1 x left over. So that's the one that stays underneath. And then we have 16 y's. If we want to know how many groups of 5 can we make, 5 goes into 16 3 times with 1 left over. So we're going to get 1 y for each of those 3 groups. So 1 y for each of the 3 groups. And then there's 1 y left underneath. So our final answer is x to the second, y to the third, times the fifth root of x times y. Make sure you put the index out here or it's not correct. If we leave that number off, we're saying it's a square root. But this is not a square root, it's a fifth root. So let's do one more. Let's do the cube root of x to the 23rd, y to the 14th. So we would never want to write all of those x's out. But if we're putting them into groups of 3, and how do I know groups of 3? Yes, that index tells us what size root we're taking. We're taking a cube root, so we're looking for cubes. Cubes are groups of 3. So if we're breaking 23 different x's into groups of 3, we get 7 groups. So we pull an x out for each of those groups, and then we have 2 left over. So underneath our radical, we have 2. For our y's, we have 14, and we're wanting to put those into groups of 3. So if we divide 14 y's into groups of 3, we can get 4 groups. So we can put a y for each of those 4 groups out front. And then how many do we have left over? Well, we have 2 factors of y left over. So instead of writing y and another y, we would call that y squared. So that's what we would get when we simplified there. So the last thing I want to mention here is just the quotient rule, which the quotient rule essentially means that if we have a quotient, a fraction under our radical, that's equivalent to taking the root of the numerator and the root of the denominator. So these two things are interchangeable. If we have a square root on top and a square root on bottom, if we have common factors, we can reduce those because we could consider that one fraction under one radical. And of course, if we have a single fraction with common factors, we could reduce. This one doesn't have common factors because these are different letters, and 7 and 9 have no common factor. So with a quotient under a radical, we can reduce those, and we can simplify the radical on top and the radical on bottom separately. Or if we have it written as a single radical, since it can be written this way, we can simplify the numerator and denominator separately. So on top, 7 is not a perfect square, so it stays underneath. But since we have the square root of n squared also on top, those cancel, so we get an n on the outside. On bottom, the square root of 9 is 3. And when we do the square root of m squared, we have 2 m's, so the square root and the square cancels, giving us an m. So the numerator and denominator separately, we use the same principles that we did on reducing when we had a product. But if we have a fraction, we can do the top and bottom separately.